everybody for joining us for the Heidelberg Joint Colloquium. So we have our speaker today who will be introduced by Hans.
Hello, everybody, also from my side. It's my pleasure to introduce to you today's speaker, Professor Carlos Allende Prieto from the Institute of Astrophysics of the Canary Islands at La Laguna. Carlos received his PhD in 1998 on a thesis on line asymmetry and line shifts in stellar spectra. You see already at that time something to do with stellar spectroscopy. From there, he moved on for 9 years to Austin, Texas, to the McDonald Observatory, first as a W.J. McDonald Fellow, later as a research scientist. After his excursion to pre-Trump USA, he returned to Europe, taking up a position as Gaia data scientist at University College London at the Mullard Space Science Lab. Worked for 2 years, then moved on a permanent position at his present institute, the ISC, on Tenerife, and was, after starting as permanent research scientist, promoted in 2018 to research professor. I asked Carlos what I should mention. I found always his central involvement in the data analysis of apogee, and currently DESI is a very big contribution to astronomy. He himself considers his most cited papers on the chemical composition of the sun, especially oxygen, as very important work. Let's see, it was oxygen and carbon, in fact. Today, perhaps not so surprisingly, we will hear more on stellar spectra, about new tricks for the analysis of stellar spectra. Welcome to Heidelberg, Carlos, and the floor is yours.
Thank you so much. Good afternoon, everyone, and thanks a lot, Hans, for this kind introduction, for the invitation. Thank you, everyone, for the hospitality. Being here for a day, and we'll stay another day. And so far, it's really very, very, very pleasant. Thanks also, Richard and Catherine, for help with connecting. I will talk about the analysis of stellar spectra, and I call new tricks rather than saying new methods or new techniques, because it's going around a lot of things that are well established, but in reality, I think we are far from getting the performance we need out of instruments, methods, and getting the right approximation. So I call them new tricks because we are still playing around with it, and they cannot be called anything else more formal. I'm in the business of stellar spectroscopy. Basically, we plug to a telescope a prism or a grating, and then disperse the light to understand what's going on in the stars, what the stars are made of. If you do this with some nice spectrograph, a nice instrument, you will see something like this, right? We hit the continuum light colors, light at all colors, and then these sharp lines, the Fraunhofer lines, that are quite prominent, some of them very strong, others very much weaker, that show absorption lines because the outer layers of the star, of the atmosphere, are cooler than the deeper layers. So we see a radiation field that is hotter, not in balance with the matter locally, and then the photons absorb light. So we see these absorption lines imprinted already. And this can be used to understand the conditions of the gas in the atmosphere of the star. And you can also, if you understand that well based on physics, then you can measure and quantify the chemical composition of the stars. This business was started all here, actually in Heidelberg, more than 100 years ago, when Kirchhoff and Bunsen worked together. They got professorships at the Heidelberg University, and they worked together, looking at the spectra of flames and then at the sun, and then they made the connection for the first time. And since then, well, the methods have evolved, and now we can do more quantitative work and measure abundances of stars of different kinds, and this illuminates a lot of aspects of interest for physics in general and astronomy in particular. We can learn about the different stellar evolutionary states of stars. Low mass stars, they don't do much, right? They just form. They are not able, brown dwarfs are not able to start nuclear reactions, and then they cool down slowly. But then when we get to the dwarfs, to the stars, we get the nuclear reactions that sustain against gravity the star, and well, a lot of things happen after the main sequence when the hydrogen is exhausted in the core, and then the stars become red giants. At different stages, well, you go with higher mass, things get even more interesting. You get nucleosynthesis in these stars, and we can, by measuring the chemical abundances in stars of different types, understand this global and complex picture of stellar evolution. And then at the top of this diagram, we will have the very massive stars, about 8 solar masses or so, that will live very short, and they will go through nuclear burning of very many different elements, building from hydrogen, helium, carbon, nitrogen, oxygen, and so forth, until the end, when just before exploding as supernovae, they will have a structure like this, in which we will have a very rich composition, variety of elements, and then these will all be dispersed around when the supernova explosion happens. And that drives the chemical evolution of galaxies, because in the Big Bang nucleosynthesis, only hydrogen and helium, plus some traces of lithium were formed, and all of the other elements basically come from stellar nucleosynthesis, with some rare exceptions of spallation in the interstellar medium. So, an interesting application, apogee was mentioned at the beginning by Hans, is that we look at the stars in our Milky Way, and we can quantify the abundances, say, for example, of oxygen. The alpha, or oxygen over iron ratio, shows in the vicinity of the sun immediately 2 distinct populations that correspond also to the different scale heights from the galactic plane, what we call the thin and the thick disk. And clearly the scales of formation are very different. The thick disk is old, formed when there was only massive stars contributing to the nucleosynthesis, and therefore we see a lot of oxygen, not that much iron. And then with contributions for lower mass stars later through the type 1a supernovae, for example, we have less oxygen, more iron, and the thin disk stars, which are lower here, have much less oxygen or alpha over iron ratios. So these are perhaps 2 of examples of the most interesting application of chemical abundances in stars. From the classical perspective, the business consists on going to the telescope, doing and taking a spectra with high resolution, high enough to resolve the Fraunhofer lines. And if you're lucky and the star is bright enough, then you can disperse quite a bit and get details, so that you can measure elements that have very weak lines. You can separate isotopic component shifts due to isotopic shifts, and measure different abundances for different isotopes and do the detailed work. As I mentioned here, classically, for over 100 years, this was done by going to the telescope, pointing the telescope to a star, and then observing that star for a while, integrating, first on photographic plates, then on other electronic detectors, nowadays CCDs, and then you get your frame. Then you go home, do the data analysis, first with, it was much more complex with photographic plates, for example. Nowadays with CCDs, it's just software dealing with image processing. And then you use physics as basic assumptions about the atmospheres of the stars, hydrostatic equilibrium, radiative equilibrium, local thermodynamical equilibrium for the line formation, and then you compare your models to evaluate quantitatively and derive abundances. This now, over the last 10, 20 years, this has changed dramatically. And I think now we are in a very interesting world in which we can learn much faster. And the picture is that the data acquisition now, instead of going to the telescopes, as I did throughout my career, now is becoming rarer and rarer. And there are, at the telescope, multi-object fiber spectrographs that do all of the job. In some cases, even robotic, fully robotic, so you don't have to do much. In terms of the data analysis, there is software pipelines that take care of all of the processing in exquisite detail, and you don't have to even look at it. And in terms of physics, well, from 1D hydrostatic models, we are moving to 3D hydrodynamical models and taking into account the departures from local thermodynamical equilibrium in the line formation. At least this is the theory. As I will discuss later, this later point, I think, is where we are really behind compared to the first two. Going now more in detail into each of these three, examples of recent instruments that set the state of the art is Apogee, for example. It was the first high-resolution spectrograph infrared that instead of observing one object at a time, it observes 300 objects at a time over a field of 3 square degrees. And well, it was revolutionary in that sense. Over a period of 6 or 7 years, this project acquired like 750,000 of high-resolution, high single-to-noise stellar spectra, mapping the disk of the Milky Way. Infrared is good for observing on the disk because the dust does not stop the infrared light so much as the optical. So this was used for a map. And before Apogee, say 10 years ago, 15 years ago, I think there were only thousands of stellar spectra ever taken by humankind. And now we move into the era of the millions, right? And homogeneous, which also makes a big difference. These are the traces of a piece of the infrared detectors. Apogee has 3 to capture the entire H band, 1.5 to 1.7 microns. And this is how the traces of different stars of different brightness look like. You can see here the Fraunhofer lines for all of them, with shifts due to Doppler shifts and changes in brightness. Another example I would like to talk about is an optical one, lower resolution, but more massive, which is the dark energy spectroscopic instrument. This is being operating now for about 4 years on the Kitt Peak 4-meter Mayal telescope. And the spectrographs of this look like this picture. They have 3 arms. They cover for 0.36 microns to 0.90 something. So very broad spectral coverage, a resolution of 1.8 angstroms. The grading, as in the case of Apogee, was a BPH, a holographic grading that makes a big difference for efficiency. Looks like this. It was unique in the sense that it was the first one of this kind done so large. Well, here you can see the throughput of this instrument. If you're familiar with this kind of plots, this is really high, around 0.7, combining through the 3 channels. And this is really unusual. It's not so high dispersion, but with high dispersion, we are more used to 0.1, 0.2. Of course, this instrument doesn't have one of those spectrographs, but 10, in order to be able to keep up with the rate of data that are provided, captured by this focal plane that has 5,000 robots with 5,000 fibers. In a matter of a minute or 2, this all move around to a precision of a micron and sit on a star or a galaxy, and then you expose and you get your 4,000 something spectra, removing some for calibration. Well, as I said, most of my career, I went to the mountain at night for periods that you were granted time and observed there at night. It was very pleasant, it's true, but now it's more efficient. We have seen that it's changing rapidly. The data also, as I mentioned, are 2D images that need a lot of calibration. So this process that was done manually before now is well studied and coded by experts. What this has changed, and why we need this automation, because what we want, of course, we want to do scientific work. It's ideal that we need to make it reproducible, optimal. So if every astronomer has to learn how to reduce the data and makes up the process, they will be different and will not obviously not be optimal. We want to make it faster when instruments like the ones I showed are coming up, and we just cannot handle the data otherwise. And well, you can see here also the scale of the surveys. I mentioned Apogee and DESI, but here we go back 4 decades or 3 decades when the measurement of multi-objects spectrograph started. We see here that the number of observations for galaxies or stars in surveys has grown from thousands to now tens of millions in a given project, which means a few years. So what would we need to do this automated analysis, which has been my focus for the last decade or so? We need, of course, model atmospheres. We need a code to solve the radiative transfer equation and compute models of the synthetic spectra. And we need then also good, robust optimization codes to find the optimal solution. What about the machine learning and AI? I will not touch on this today. There is a lot of people trying to use these methodologies, but for the vast majority of the part, they rely, of course, on the same physical models that attach to the first 3 points here, right? So it's less just trying to speed up something that works with the model atmospheres, radiative transfer, and optimization. Model atmospheres, there is a recent review by pools, including myself, in which and Herrero, in which they go through all of the existing codes, abundances to study chemical evolution or stellar evolution, need mostly cool stars. So if we focus on those, basically we have Kuruts and Marks and Phoenix, the 3 mainly codes that exist. It happens that Marks and Phoenix, well, both Kuruts and Marks are from the 70s. The original versions have evolved over time, but Phoenix is a bit more recent. But both Marks and Phoenix are not public codes, which, this I think goes a little bit against what we would like for current modern scientific endeavors. Models, of course, can be taken from existing grids. One can interpolate in those with some limitations, or for the codes that are open source, which basically are Kuruts and T-Lasti for cool stars, one can compute them. There are 16 grids with limitations of one kind or another. I just keep this here for reference. One can interpolate, but until recently, we only had 2 tools publicly available that based on a linear interpolation. One for Marks from Masseron, and another one that I wrote a long time ago in IDL. And now there has been a recent code that uses neural networks to interpolate in several of these grids at the same time. So it's very flexible compared to the existing ones and fast. The models can be computed afresh only for a few cases like the Kuruts or the T-Lasti, but the T-Lasti is still not fully equipped with all of the atomic and molecular data needed to do full-blown model atmospheres. So basically, we are left with Kuruts unless we are within the Marks or the Phoenix groups that have developed the model atmospheres. Regarding spectral synthesis, radiative transfer solvers, here I think we are in better shape. There is really many more codes, and these are the most heavily used ones, and they are public, open source. The ones I put down here on the right, they use these ones here on the left, which I think all but one are written in Fortran. And even Fortran 77. And the ones on the right are more modern language interfaces, but they use some of those in the left. They are not a full independent codes. I will talk a bit about simple because I want to promote it a little bit. I've been working on this for some years now. It's this interface to the code sing spec. It's written in modern Python 3. It has a minimal command line interface. It works with Mars, Kurut, Phoenix, or T-Lasti models, LTE or non-LTE for the case of T-Lasti. And it tries to help the user to be practical, and rather than having to go through a bunch of courses and work with experts for some time, you can really use it with minimal knowledge. Basically, if you give it a model atmosphere, the model contains the atmospheric structure, the chemical composition, some other parameters that are needed. You can just give that file and a wavelength range, and it will do clever decisions for you about the sampling and about which molecules to leave in, which molecules to leave out. I have here just a simple example of how to use it. Just align like command number 2 here will create a plot and even identify the main transitions and tag it for you. Then the next step, once you can compute model spectra, is to compare your data to the models to infer the parameters you want, the atmospheric parameters of the star and the chemical abundance, right? For that, there is also many, many more codes, but I'm mentioning here the ones that have been more used, SME and iSpec. And FERRE is the one I wrote and was used at the core of the Apogee reduction pipeline to measure the parameters for these 750,000 stars and the abundances for some 20 elements. Now I have been working on a new one that I call BAS, which is more flexible, perhaps not as fast as FERRE for some applications. For massive ones, are much easier to get started with, or for small projects, is really easy. Other examples are listed here. Most, but not all, are private code. I will mention briefly FERRE. It's Fortran 90, parallelized with OpenMP. It's written in a way that is really n-dimensional, so you can think of the typical parameters of an atmosphere, temperature, gravity, metallicity, and then you can have all of the elements that you want as more dimensions. The only limit in practice is that to be fast, this tries to avoid computing the radiative transfer on the fly, which is the slowest part, and then simply you pre-compute a grid and then interpolate, storing the grid in the RAM memory of the computer. Then the limit becomes that, of course, your RAM has a limited size. Then if you go beyond 7 or 8 or 9 dimensions, you start getting in trouble with current computers. But you can also store it in a database, and disk access also is improving in speed. It was successfully used in Apogee, and now it's being used in DESI or Weave. When it comes to finding the optimal parameters, it has built in some classical methods, and also MCMC, which gives the better error bars, but it's more expensive in terms of time compared to the other algorithms. In the case of FERRE, we had an algorithm or a methodology in which we run first with a 6 or 7 dimensional grid, fitting the entire wavelength range. I see here a small piece. And then after that, we did a second pass fitting the abundances of individual elements. There was an increased complexity because the instrument with the wide field and so many fibers had a wavelength dependent and fiber dependent TSF that we have to deal with. But of course, this machinery may be a bit too heavy for one or few stars. It's necessary when you have thousands or tens of thousands or more. But if you have 3 stars, then may not be ideal. And for this, I've been working on a new code. Problems also is that FERRE does not derive rate velocities on the fly. Also, if the resolution is low enough, then you cannot resolve individual lines, and then dealing with blends requires more dimensions. As I mentioned, if you go beyond 7 or 8 dimensions, you probably get out of RAM. Well, in some cases, there are gridding effects that we noticed. So for that, a new tool that can be used, also, as you see, promoting, is this bus has nothing to do with the politician or the rapper. It's a Bayesian algorithm in simple. Simple is the other code I mentioned earlier on. And here the trick is, in order to save time compared to doing the interpolation on the fly, you try not even to do the interpolation. You just have a grid with enough models thrown in at random that you can use them directly in a Bayesian scheme to infer the optimal parameters and the error bars. So, but basically you just have your grid of models, you compute the likelihood, and then you evaluate the more likely value for each parameter, and then naturally you also get the covariances in a simple calculation. These pre-computed models need to be many more than in a grid where you're going to interpolate, because here they have to be dense enough to sample statistically the regions around where the likelihood is high enough. But it's straightforward. And of course, it means you do, in most cases, a lot more work in terms of computing time of model evaluating than in the other algorithms, but it gives you also new opportunities for parallelization, because the number of models to evaluate is always the same. That means, trivial parallelization, and I think this is a strength for when we are looking at GPUs where we have thousands or tens of thousands of threads. In the case of Ferre, when we use regular grids in 2 dimensions, it would look something like this. Now with BUS, it will more look like the red sample there, that the models are ready to evaluate the likelihood without even further interpolation. The code also has a bunch of tricks to really going towards full automation, which is, I think, the goal I'm looking for here. First, the code has some piece of code that will look at the header of data and try to figure out where it comes from, like the resolution, the instrument, etc., and then looks into a database and then chooses from a pre-computed grid with the right resolution, with the right wavelength coverage for that instrument. For now, we have sample grids that cover star types from K to A. This is A will be like star like Vega, a white star with 10,000 Kelvin of effective temperature. A K will be something pretty cool, low mass star with 4,000 Kelvin or so. So for now, there are already grids available for the INT, for a couple of instruments on Hubble, for Osiris on the GTC, for DESI, or for Gaia XP. Actually, we're using this for processing the Gaia low-res spectra. The code incorporates cross-correlation and template matches for measuring radial velocities, Doppler shifts in the spectrum on the fly, which is very convenient because then you just don't have to worry about that part. And it can also do on-the-fly reddening corrections due to the interstellar medium effects, dust reddening. And even there is tools for self-evaluation, so it can itself build simulations, injecting noise and trying to estimate internally the error expected, at least under optimal ideal conditions without systematic errors. And these are test results in which I have a grid with 3 dimensions for data that look like the Hubble, HST, STIS low resolution modes. And this is some kind of automatic plot that will show you the error bars and that. This is for Gaia XP, spectrophotometry with super low resolution spectra. And in this case, there are 2 more dimensions. It's the stellar reddening and radial velocity, so it's 5D. Another an example of how this would be used, you just call BUS with the file, and if it is a file produced by one of the instruments in the collection, which hopefully will grow over time, then it identifies which instrument comes from. In this case, the STIS on the Hubble. It will measure the radial velocity. Well, it will first do a fitting, an initial fitting to identify the type of star, choose a template, then by cross correlation or template matching derive a radial velocity, then correct the Doppler shifts and get you back a solution. This is an example for the Hubble data, how the error bars from simulations will be reduced as you increase the number of interpolated models. At some point, it will saturate, but it looks like for this curve at the bottom is for 3 dimensions, the second one for 4 dimensions, and the second one for 5. That as you have more dimensions, of course, to have similar densities and similar accuracy in the solutions, you need to increase the number of interpolated models. But these numbers are quite easy to handle on typical computer. What about the physics? I think this was the last item I wanted. I had in my list in this list of items that need to be or that we are tackling to modernize the business of measuring chemical abundances in stars. First, non-LTE and hydrodynamical model atmospheres. This is being known for many decades to be the culprit to get accuracy in abundances, and to go from the current standards will be more like 10% to few percent that we really want. And where, in that change, that we will discover a lot of new interesting things. Non-LTE. Well, the methodology that we have will work either with LTE or non-LTE. So it's just a matter of being able to compute non-LTE models. There is already some progress in Apogee, for example, or in Gala. Now there is massive analysis done that incorporate non-LTE grids for a bunch of elements, but it's still far from being complete. We have also found in recent years that non-LTE effects is when radiation is no longer coupled to locally to matter, and then you cannot use the Boltzmann equation to compute the populations of the atomic levels. Then you need to consider the effects of radiation far away, and everything becomes much more complex. We have found that non-LTE effects can propagate from one element to another, because if you have non-LTE effects, the radiation field in one element may change at some wavelengths that will affect another element. So this has to be done together. One big problem here is that the models, like it used to be with the model atmospheres, before the models, the model atoms and the non-LTE atmospheres are also normally private, kept private, not made public. And this, I think, hinders progress because it's not shared with other groups. Regarding hydrodynamical models, we have the first indications that this was important from the 80s, when it started to be developed, and then we changed the very simple 1D hydrostatic models where nothing moves and everything is homogeneous at any given height in the atmosphere, into these hydrodynamical, in some cases magneto-hydrodynamical models that considers the time evolution and the surface structure of the stars, like we see here for a solar-like star, the granulation pattern of scales. The size of those granules is thousands of kilometers. For decades, we have seen only these models applied in punctual cases to one star or another to understand these effects. But the promise of this becoming mainstream and being used by everyone has not been fulfilled. Now, in recent years, we have transitioned from individual models to small grids. Of course, these simulations take a lot of time to do, and then computing the spectra for them takes a lot more time. But sadly, these mini grids of models are still private. Recent action, well, not so recent action. There is a staggered grid that initially had 37 models, and there is a very recent paper from last year that expands this to 150 or so. But I believe these models are attached to projects. Still, It's not something that anyone can use. The CIFIS grid also has about 85 models, but it's still private. And there is a new program now to produce many of these models en masse. Actually, the project is also led, I think, here at the Heidelberg Max Planck for Astronomy Institute. And they already mentioned in a paper, in a recent paper, and in the web page, that they already have 50 models, and this hopefully will grow over time. And I think the intention here is to make them public. But it's few models. How do we deal with these models? It's more computationally intensive to evaluate the spectra from them, of course. And then you have to cover the entire types of stars with just maybe 100 models or maybe a few hundred, which is very coarse and will make it difficult to carry out very high accuracy interpolations. Well, one possibility that was explored by Bertrand, Delis, and others in 2023 was not to interpolate in the spectra, but to interpolate in the ratio between 3D and 1D, which compresses the range. So being smaller numbers, you may expect more accuracy with this. But this I don't think has been applied only to LTE calculations, and not we still need non-LTE, and that's a critical point because it has been case that sometimes if you consider 3D models but still LTE, your answer may be farther away from reality than using a 1D model in LTE. And this is because the non-LTE corrections in the 3D structures become generally larger. You have deeper or larger variations of temperature, and then non-LTE effects become enhanced. So one has to be very careful and understand when non-LTE effects are expected in order to use them in LTE, or ideally build them fully or compute the spectra for them in non-LTE. In that regard, I just list here a wish list of the questions that I think are really, really important in order to make further progress on this matter. One is whether we can use horizontally average along lines of constant optical depth 3D models, or they are useless, because in this process of averaging, a lot of information is lost. And this has been used in recent literature, and nobody has studied yet if this is good enough. Another question is, the problem of solving the radiative transfer in the 3D, and that is not really 3D, but 4D, because you also have to do that in a snapshot as a function of time, becomes of, maybe 10 to the 4, 10 to the 5 times heavier than do it in 1D models. But when you go to non-LTE, you have to do that many times in order to iteratively solve the coupling between the radiation and matter. And then the problem really gets out of hand. And this is why we still have only 3D non-LTE calculations for very limited cases. Can we maybe use a shortcut like the 1.5 approximation that exists for maybe 2 decades, but it has not been used, or when it has been used, it has never been done with a serious evaluation of the errors that we make adopting that? And then another question I have is, can we at least use 1.5 for the SORMA solution in 3D non-LTE, to solve the radiative transfer? And this is a basic question that I recently looked in the literature and nobody has answered yet. This is all I have. There is here a summary I will briefly go through. So to clarify the take-home message, that spectroscopic instruments have changed very much, and now we can go really fast and put our efforts and our attention to other sites, because the instruments work basically on their own. I mean, we still have to fund the construction of the instruments, fund the operations, and in some cases go to the telescope to do this, but it's not something that will take a third of our time or a tenth of our time. We can really turn into the physics and not pay attention to this anymore. We don't yet have fully automated software to do this spectroscopic analysis, but I think that's coming up. We're getting close, although some efforts are needed on this front. And I think where we should be putting really our efforts, and the current generation should be looking to contribute more, is in the theoretical, in the physics side, to really improve the models, to really make a reality 3D normality in practice, and make sure that we understand the errors, the systematic errors that we have when we use these hypotheses, because of all of the approximations they also involve in terms of missing data or missing processes. And if we don't use it, understanding why or what kind of errors we suffer from that. Thank you very much.
So we'll open the floor for questions. Thank you for this talk. Questions, especially from students and postdocs.
Hi, Carlos. I'm not a student, but okay. On your second point, I agree that with all these surveys of millions of stars, we need something automated. But what about the peculiar stars that may not fall into your grid, carbon stars, chemically peculiarly enhanced? So how much human interaction is still needed to also keep the fun a little bit in the stellar spectroscopy?
Yeah, obviously, though, I mean, you can do this fast or this survey work where you expect the vast majority of the stars will be within a range of parameters, right? But of course, there is many instances of stars that really are special, that are have very different compositions, that have strong gradients in chemistry, that have strong magnetic fields, and those cannot be analyzed in mass, and they will need special attention always. I think so. But I mean, developing a lot of these tools, except for the automated ones, will benefit as well those models that we always need detailed attention.
More questions.
So could you go? Can you hear me? Yeah. To your slide on BAS, I think it was BAS. The one with the this one. No, the one with the points. Yeah. So here I'm not too sure what you're doing, because from this graph, the impression I have is that it's not so much the irregularity that changes, is that you have more points over there. So
yeah,
is it the fact, or is it because it's in 2D and we don't really?
Yeah, you have more points and they are randomly distributed.
Yeah,
that's the only difference.
Okay. Sorry. What is the main factor, that you have more points, or the random distribution of the points that helps you to better sample?
You need both.
You need both.
You need both. If in order, I mean, basically you're trying to do MCMC. It's not, but it's a Bayesian algorithm in which, instead of sampling with MCMC in a clever way, you just sample in a brute way. You just sample everything uniformly. I mean, you can trivially build in priors, of course, but I mean, in the most simple case, you just have flat distribution everywhere, and the idea is that this sample will be enough for any star with any noise, so that will always be high enough and random enough in the area that the star of your interest will fall, so that you sample widely like crazy from a start, but then you don't have to sample anymore. All of your models are just there. Of course, you can then build refinements on these. One easy thing is that you do a very coarse sampling to get where in your parameter space your object is, and then you go and read only the fine sample models around that region. But I mean, in principle, the code is just like 3 lines in which you have everything sampled in very detail at random, and then you just evaluate the likelihood with all the models. So, it's kind of infallible in the sense that your algorithm cannot get lost. You will always have everywhere inside the domain the likelihood for every model. I mean, in general, it sounds a bit crazy in the sense that you may have there 10 to the 5 models, and with the other code, you may need only, I don't know, 100 models or 100 evaluations. And here in this algorithm, you will go and evaluate 10 to the 5 always. But the thing is that if you have, 10 to the 5 threads, how much compute work is always the same, and it will always be in parallel, so it will take the same time.
So question in the back.
Regarding sharing the code, do you want people to share their codes for other people to use them? Or do you want other people to contribute to the development? Because that would require some organization. Otherwise, it will quickly get a mess.
Yeah, I think ideally for scientific progress, everything has to be open. Data has to be open, codes have to be open, so that anyone can reproduce what we do, right? With the complexity of models these days, really describing some algorithm, describing a process in a paper is rarely enough to anyone to reproduce it, right? So ideally, everything has to be released as a form of code or data. Of course, in the case of the model atom, or in the case of the hydrodynamical simulations, I think the most important step is really to share those models. Computing them requires really an extreme level of expertise that many will not even have. So there will be very few of those interested in using the code, and many more or interested in using the data themselves. So I think that's the priority. But ideally, you will have also the code.
All the questions are on this side. I have 2 questions. One following on the previous speaker about models and code publication. What kind of incentives do you think are missing in the field that would encourage authors to publish those codes, either carrots or sticks? And the second question, you didn't talk about machine learning, but do you think that there is any areas where machine learning methods can address some of the challenges that you're facing?
Yeah, I think it comes in a lot of cases down to education or discussion, right? A lot of people in the past were hesitant to make public their codes or their results, thinking that others could then use them and they will lose the advantage they have for developing. We have seen, I think, over the last decades that usually that's not the case. It's the opposite around. That is the most effective way to get results quickly, to make progress, is working all together and releasing as quick as you can. Maybe just try to identify a little niche that you can do first, and then if your tool is really powerful, try to release it as soon as possible. We've seen it, and when people hold on to the tools, normally they are the first that lose the benefit because it's used very little, and then the debugging takes much longer time. I think it's a very positive thing that we just do the statistics, and we will realize, and perhaps it's the older ones that have to talk to the younger ones to open their eyes. Look, don't be afraid about this, because now it's common practice, and this is the way it works.
Yeah, just to make a comment on the open source. One other thing that I think stops people from making codes open source is 2 things. One is that if you have a not so well documented code, then people can easily make wrong results with them and then publish them. And then if then these results are being identified as wrong, then the code is being blamed, and therefore the author is being blamed rather than the people who actually use the code. That's a fear that people may have. Another thing is that if you don't write sufficiently accessible documentation, is that you get bombarded by many emails, which is exhausting. And so my recommendation is to anyone who has a code, reserve 1 week of time and do nothing else than writing a very extensive, detailed, and good manual. And then you have many advantages. People won't misuse your code. People will actually love reading the manual, and will praise you for writing the manual. It will be you will receive far fewer emails that you have to answer. And the final advantage is that people will actually use your code well, find the actual bugs, and then email you, and you will be able to find your bugs more quickly. So, but it requires a dedicated effort of 1 or 2 weeks sitting down and actually writing that, which is a lot of work, but it's worthwhile. So
I fully agree. And I mean, it may be a substantial effort, seen as 1 week or 2 weeks, but normally, if you compare that, they divide that by the time that it takes to develop, it will be very little.
I think there was a question online.
Yep. I'm just taking a question online from Richard Hopper, which I'll read out for clarity. So Richard writes, more of a comment than a question. As Carlos mentioned, average 3D models, they are not really a huge step forward, as one still needs to compute a 3D hydro atmosphere in the first place, which is the bottleneck anyway. About using the 1.5D approximation for 3D NLTE spectrum analysis, this is actually not necessary, as the full 3D radiative transfer is not the bottleneck. In most cases, it is the opacity calculation, which is the bottleneck, or the radiative rate calculation when using complex model atoms. So end the quote. I pass the question on to Carlos.
Yeah, I don't have much to say. I mean, wherever the bottleneck is, we have to identify it and go after it and identify shortcuts. So it's no longer the bottleneck.
Any final questions? If not, then let's thank Carlos again. There will be.
Yeah, like always, we have planned for the students, perhaps also young postdocs, for drinks with the speaker right now. So whoever is interested to join, please come down and talk to us. Moreover, we have arranged for dinner at the Dorfschenke at 7 p.m. later. I sent around a mail. I got already some indications of interest. If somebody spontaneously still decides to join, also come here. Thank you.